we are very pleased to receive Anna Marina today, who is visiting from Perimeter. She did her postdoc, her PhD in Harvard with Andy Strominger. And she's done a lot of work on infrared structure of gauge symmetries. And she's participated to the development of the celestial holographic program. And she's here to talk about the celestial W1 plus infinity symmetries and asymptotic charge dynamics. The floor is yours.
Thank you very much, Charles, for the very nice introduction. It's a pleasure to be here and actually in person and be able to tell you a little bit about my recent work with Laurent Fidel and Daniela Franzetti from Perimeter. Okay, so this story starts with the work of Strominger and collaborators. So it's been known for a couple of years now that gravity and gauge theories in the infrared are governed by a set of equivalences. The main subjects of these equivalences are soft theorems, asymptotic symmetries, and memory effects. So soft theorems relate scattering amplitudes with and without low energy massless particles. Asymptotic symmetries, and in particular asymptotic symmetries of asymptotically flat spacetimes, are gauge symmetries or diffeomorphisms that don't fall off to zero at infinity, and hence are associated with non-trivial asymptotic charges and have a non-trivial action on the asymptotic phase space. And so one would expect that the observables in asymptotically flat gravity, for example, to be organized in representations of these symmetries. Memory effects are presumably or are believed to be observable signatures of these asymptotic symmetries, and roughly speaking, they say that there is a non-trivial change in the asymptotic gauge connection or metric under the passage of gravitational radiation. So the connections between these three subjects are captured by this diagram here. So first of all, the connection between soft theorems and memory effects is given by a Fourier transform. So one should think about the soft theorems as representing the Fourier space version of a radiative solution of the classical equations of motion in gravity or gauge theory at low energies. Okay. Now, the relationship between soft theorems and symmetries, in particular in gravity, was realized only recently through the work of Strominger and collaborators, and is given by a conservation law. So how does this work? Well, it's been known since the 60s that asymptotically flat spacetimes have a much bigger symmetry group than originally anticipated. The symmetry group consists of, among others, angle-dependent translations in the null direction. And so these are associated with some vector fields, which can be used to construct charges. And the conservation of charges in time, when written as a Ward identity for the S matrix, turns out to give rise to the soft theorems. Now, finally, the asymptotic symmetries and memory effects are related through the fact that these observable shifts in the asymptotic metric or gauge connection can be undone by a large gauge transformation. Now, today I'm not going to have time to discuss these interesting connections to the memory effect, and I'm mostly going to be focusing on this relationship between soft theorems and symmetries. And so one first question one can ask is whether to what extent do asymptotic symmetries determine gravitational, for example, in gravity, gravitational radiation. And so the discussion here has been focused on the leading term in the soft theorem, but one could wonder whether subleading terms in the soft expansion, which one can imagine to give better and better approximations to the scattering amplitude, whether those are also associated to soft to symmetries of some sort. And it turns out that the answer to that question is actually yes. And so while we know that the leading soft graviton theorem is associated with these angle-dependent translations or super translations. It's also been known for a while now that the subleading soft graviton theorems are associated with another enhancement of the expected Poincare symmetries in asymptotically flat spacetimes, namely an enhancement of the Lorentz group to Virasoro. So how do you understand this? So a simple way to think about this enhancement is to realize that Lorentz symmetries act on the spheres at infinity or on cross-sections of null cones as global conformal transformations or global conformal symmetries. So just in the same way as conformal symmetries in 2 dimensions are enhanced to Virasoro, Lorentz symmetries in 4 dimensions can be shown to also have to obey similar enhancement. And the signature of this enhancement is the subleading soft graviton theorem. Now, you may wonder, well, what is the generator of this Virasoro symmetry? And it turns out that one can construct a particular mode of the subleading soft graviton whose insertions in the S matrix behave exactly like insertions of the stress tensor in a 2-dimensional conformal field theory. Now, if we think back about the history of ADX-CFT, it's been known about 10 years before the proposal of ADX-CFT that the asymptotic symmetries of asymptotically negatively curved spacetimes in 3 dimensions are also infinite dimensional. And of course, in retrospect, this was a very important observation and a very important kind of step in formulating a holographic correspondence in that context. Now here we are in asymptotically flat spacetimes, but perhaps history should teach us that one should take this enhancement of Lorentz symmetry to Virasoro seriously and try to come up with a way of reorganizing the observables in gravity according to these symmetries.
Very good.
Yes.
Can you remind me, the Virasoro on the previous slide, does
Yeah.
that have a central charge?
Oh, it's a great question. So I should say that today I'm going to focus on the 3-level case, and at 3 level there is no central charge. But this is an interesting question. For example, one can go to loop orders and study loop corrections of these soft theorems, and in that case, one would expect perhaps to see some central charge. But at the moment, there is no central charge. Yeah.
I have a very simple question. I don't know what an asymptotic symmetry means. Like, I know what a global symmetry of space-time is. It's an
I will, in the second part of the talk, I'm going to spend more time in explaining that, and maybe just bear with me for a moment, and we can come back to this question. Any other questions? Okay, so right. So the idea now is to try to use these symmetries, these infinite dimensional symmetries, to write down, to reorganize observables in gravity. And one of the proposals is that in the case of massless scattering, where we know that the fundamental observables in gravity are just scattering altitudes, and these are just functions of on-shell momenta, and each on-shell momentum, as you know, is labeled by an energy and a direction. And this direction can be thought of as a point on the celestial sphere. So one can take these asymptotic momentum eigenstates and turn them instead into boost eigenstates. So a boost eigenstate can be obtained by taking a Mellin transform with respect to the energies of these external particles. And so what one obtains now is, instead of a momentum eigenstate that is labeled by an energy and 2 angles or a point on the celestial sphere, which I'm representing here by these z and z bar coordinates, complex coordinates, one obtains a state that again is labeled by a point on the sphere, but where the energy is traded for a scaling dimension. Okay, and so by then computing the scattering matrix in this new basis, we obtain observables that transform covariantly under the Lorentz group. So, and in particular, these observables now manifestly live on a two-dimensional sphere. And so the S matrix in the spaces of boost eigenstates has been come to known as a celestial amplitude. And they will be one of the main sort of observables we'll be dealing with in this talk. Now, so far there has been efforts in trying to understand what this holographic dictionary is. So I should say again that these celestial amplitudes are believed to be two-dimensional observables for quantum gravity in four-dimensional asymptotically flat spacetimes. And so the next step we would want to do is to understand better what the holographic dictionary is between this two-dimensional theory and this four-dimensional theory of gravity in asymptotically flat spacetimes. And so far, most of the things we have learned have followed from translating facts we know about amplitudes in four dimensions to properties of two-dimensional conformal field theories, of this two-dimensional weird celestial conformal field theory. Now, one thing that we know, and it follows by construction, is that Lorentz symmetry in the bulk acts as global conformal symmetries of the two-dimensional sphere. What's more interesting is that we know that in the bulk we actually have full Poincare invariance, so we also have translational symmetry, and that on the celestial sphere acts as some kind of new set of global symmetries that, roughly speaking, relates correlation functions involving operators with shifted dimensions or weights. Now, moreover, in addition to Poincare symmetries, we know that celestial conformal field theories also obey a large class of symmetries that follow from soft theorems in the bulk. And these are generated by so-called conformally soft currents, and I'm going to return to them because this is what the talk is going to be about. But roughly speaking, these currents are associated with negative dimension operators in this two-dimensional conformal field theory. Now, there's other facts that are known about celestial amplitudes. One of them is the fact that there is an interesting story that allows one to ask infrared divergences of scattering matrices in four dimensions into some kind of like vertex operators of so-called Goldstone modes in the celestial conformal field theory, and correlation functions of these Goldstone modes actually capture these infrared divergences in the bulk. So this can be shown. And moreover, if one restricts to 4-point massless scattering in general at all loop orders, one can translate various properties, low and high energy behaviors of such 4-point massless scattering to analytic properties of the celestial amplitudes on the celestial sphere. But today, I am mostly going to be focusing on this relationship between soft theorems and symmetries. And I'm going to try to explain how these negative half-integer dimension operators are actually associated to symmetries and give them actually a bulk interpretation. So the outline for today, in the first part of the talk, I'm mostly going to be reviewing facts about, first of all, universal aspects of scattering amplitudes in 4 dimensions. I'm going to talk about soft and collinear factorization. And then I'm going to describe how these give rise to properties of celestial amplitudes, and then use conformal symmetry to make some prediction about the operator algebra of these symmetries, or these conformally soft operators. So after that, we will see that sort of we go to the celestial sphere and we use the machinery of conformal field theory to arrive at some kind of, perhaps one would think of as exotic symmetries in the celestial conformal field theory. We're going to see that this is going to be some higher spin symmetry. And of course, in 4-dimensional Einstein gravity, such symmetries have not really been known of before. So the main part of the talk is going to describe how to actually think about the symmetries in Einstein gravity, and we're going to identify some explicit asymptotic charges, and we're going to see that they give rise to a tower of soft theorems, and that their algebras indeed turn out to be a higher spin symmetry amplitudes. Okay, so let me start off by describing again what the soft limits are in more detail. So we have a scattering amplitude of massless particles plus one graviton. Okay, so the graviton here I'm labeling as the momentum of the graviton I'm taking to be omega times q hat, where q hat is some null vector, and omega is the energy of the graviton. Now, at low energies omega, the amplitude can be expanded as a Taylor series in omega. The leading term in this expansion is the so-called soft graviton theorem, and is the thing that is associated with the super translations I mentioned at the beginning. The subleading term in the expansion is associated with these super rotations or the enhancement of Lorentz symmetries to the Raclariu, while this tower of sub-leading soft theorems, what one should think about as is to give better and better approximations of the scattering amplitude with a finite energy graviton. So in some sense, if you were to know all of these corrections, you would have all essentially information about an amplitude that has a finite graviton insertion. Okay, so these soft, yes.
Are there non-perturbative contributions? Like if you knew the whole expansion, is there a proof that you can resum everything?
That is a great question. I think it's an open question at the moment, but it's I think the question is isomorphic to whether the power of soft currents we're going to see later on, whether they form a basis in for essentially plane waves in gravity. And that question is actually an open question, but I will comment on it at the end. Yeah, that's a great question. And I should say that this expansion should hold in the full theory. We don't have to restrict to tree level, although in this talk, I will be restricting to tree level because in that case, as we'll see, the story is much cleaner and actually the loop corrections are not fully understood at the moment. So, and another thing to mention is that while the leading and subleading soft graviton theorems in pure gravity are universal in the sense that they don't depend on the matter content of the theory, the subleading corrections, they will depend on particular couplings of gravity to matter. And so you would have to compute them independently in your favorite theory of gravity. And this calculation in principle is not straightforward. And so, okay, using modern amplitude techniques, even just the subleading soft theorem was only very recently computed in around 2014. Okay.
Is there assumed cutoff from the internal gravitational loops and in terms of this expansion exercise?
Yeah, so that's a good question. If you have loop corrections, there will be dependence. There will be corrections to this starting at subleading order to these soft factors, and those will depend on the infrared cutoff. But at tree level, there are no internal graviton loops, and hence there is no.
So this is the tree level.
So, well, here I'm not telling you what these SNs are. So this expansion holds at all loop orders, but yes, the SN at each n, which corresponds to a particular order in the subleading soft expansion, they will also depend on the cutoff. When you go in the full theory, they will have corrections that will depend on this cutoff. So yeah, if you want, there should be the argument here for the most general expansion would involve a cutoff. But here, as I said, the story I'm going to tell you today is about the tree level intense. Okay, I'm not even telling you right now what the soft factors are. I'm going to tell you what they are from a two-dimensional simple argument involving just using conformal symmetry. But in principle, this is a well-defined expansion for scattering. Okay, so how do we map? What does this expansion? How does this expansion look like in the celestial conformal field theory? Well, naively, you may say, in a conformal primary basis, we have traded the energy for a scaling dimension. So how do we take a low energy limit? So what does it mean to do a low energy expansion for the celestial amplitude? Now, it turns out that there is actually a way to extract turns in a low energy expansion in the bulk from a celestial amplitude as follows. So what the prescription is to compute a particular residue of the celestial amplitude as the dimension of the operator that corresponds to a graviton becomes negative. So this is done here. And it turns out that computing this residue extracts for you a particular subleading term in a low energy expansion of the scattering amplitude. And in particular, computing the residue at a particular negative integer dimension of this insertion will extract a particular sub-leading contribution at the corresponding order in the scattering amplitude. And there is a simple way to see this, which starts from the definition of the celestial amplitude as a Mellin integral with respect to the external energies. Split these integrals into a low energy part and a high energy part. And then for the low energy integral, perform a Taylor expansion of this operator of finite energy. And upon doing so, one can see that a particular subleading term in this low energy expansion will give rise to a pole at a particular negative integer dimension of this operator. And then one can also argue that the high energy part of this integral actually won't give rise to any such poles. And so the only contribution we have from low energy sort of particular modes in a low energy expansion comes from residues of these operators at negative integer dimensions. So here we have a map between the soft expansion and bulk and insertions of increasingly negative dimension operators in the celestial conformal. Okay, so that was number one, universal aspect of celestial amplitudes. The number two aspect has to do with collinear limits. So for scattering amplitude, what is a collinear limit? Well, it's a limit in which you have two asymptotic massless particles that become collinear. So their momenta become parallel. And in that limit, it is known that to leading order in this close, in the collinear expansion, the amplitude factorizes into a factor that is analogous to the soft factor, but now depends on the momenta of the particles that you're taking to be close to one another, and the amplitude involving the same particle, but now with the momentum that is the sum of the two momenta you are taking to be parallel to one another. And so, so here is a picture where I'm illustrating this. So in gauge theory, you can take two positive helicity gluons and take this collinear limit. Upon parametrizing the massless momenta, as I showed before, in terms of an energy and a point on the celestial sphere, one can show the splitting function, which has been known for a long time in quantum field theory, takes this simple form. So of course, it's a function of the position of the points towards which these two particles point on the celestial sphere, which is captured by this 1 over Zij term here. And then it's a function of the energies of these external particles, as one would expect, where I'm calling omega p as the sum of the energies of the external particles. So remember, as you're taking particles to be collinear, right, they will become proportional to the same null vector pointing to a particular point on the sphere. So it can be either one or the other, either Zi or J. And then the energy of the resulting joint sort of gluon or graviton is going to just be the sum of the two external of the two gluons of graviton. And similarly, in gravity, you can do the same thing. There's just the splitting function now takes a slightly different form, as shown here. So if you stare at this and you take a simultaneous sort of, if you work in Lorentzian signature in the bulk, where Zij and Z bar Ij go to zero simultaneously, we can see that the difference between the gauge theory splitting function and the gravity splitting function is that in gravity, we seem to not be having a divergence as the two particles become collinear, which is the statement that in gravity, there are no collinear divergences. But nevertheless, you're going to see in a moment that it's useful to actually think about the Z and Z bar as real independent variables and consider so-called holomorphic or anti-holomorphic collinear limits, in which case one can think about this prefactor as actually blowing up in a limit where one takes Zij to 0 independently from Z bar ij. Okay, so now naturally these collinear limits, if one recasts them as a statement about celestial amplitudes, well, what are they going to be? They're going to be some kind of operator product expansion limits for celestial amplitudes. So what do I mean by that? Well, naturally these two particles, they're pointing towards particular points on the celestial sphere. And so in the collinear limit, as we bring them, as their momenta become parallel to one another, this amounts to the statement of taking the two operator insertions on the celestial sphere to approach one another on the celestial sphere. And this is the same as the operator product expansion in a conformal field theory. And indeed, one can show by direct calculation that these leading splitting functions in both gauge theory and gravity map into operator product expansion like expansions in the celestial conformal field theory. And in particular, we see that the Zij dependence remains untouched by a Mellon transform, while the energy dependence turns out to map into some particular functions of the external dimensions. So here, these B, X, Y are Euler beta functions of the external dimensions. So it's not going to the specific form is not going to be super important in this talk. What you have to keep in mind is that these mathematical functions, they have poles at negative integer dimensions whenever one of the arguments become a negative integer dimension. That's the main thing to keep in mind about these functions. Now, this calculation I have shown you follows straightforwardly from just taking the splitting functions in the bulk and taking Mellon transforms. And indeed, this is how these expansions have been originally found by direct computation. But what's interesting is that actually one can arrive at the same statements just purely based on a symmetry argument in the celestial conformal field theory. So first of all, one can note that these operator product expansions, if one thinks about them on this two-dimensional sphere, they are completely fixed by conformal symmetry alone. So the fact that we only have a leading pole in Zij here can be shown to follow from requiring that one has a local bulk. But once you know that your leading contribution to the OPE is just a simple pole in Zij, essentially the form of this prefactor is essentially fixed, right, by conformal symmetry, because we know that here we have gravitons, namely helicity two operators of dimension delta I delta j. So the only sort of prefactor, once you decided that you can only have a simple pole in Zij, this is the only thing you can write down and have an operator of spin 2 on of helicity 2 on the other side. Okay, and the only thing that is not fixed is actually this coefficient. It's sort of similar to what one would get in a conformal, two-dimensional conformal field theory. But what's interesting is actually that this operator product coefficient can be fixed by the symmetries of the celestial conformal field theory. So they are determined by consistency of the OPE with the, in particular, sub-leading soft graviton theorem. So what do I mean by that? Well, one can show that the sub-leading soft theorem has a particular action on an operator in the conformal field theory, and imposing that action is a symmetry of this OPE, namely that by computing the variation of both the left-hand side and the right-hand side with respect to this action, one gets a consistent equation. One can show that this the C function has to obey a particular recursion relation. And this recursion relation turns out to just have one solution, which turns out to be this particular Euler beta function, which I showed before. If you want to think about this differently, is that this sort of symmetry action is a particular case of imposing associativity of the OPE in the celestial conformal field theory. So this is just saying that the OPE of two positive helicity gravitons in the celestial conformal field theory is associative. And associativity imposes a non-trivial constraint on this leading OP coefficient that is solved by this Euler beta function. Okay, but now this is just a statement about the leading term in this expansion. So you may wonder, what about subleading contributions? And indeed, if you think about conformal field theory, we know that there is to each primary. So here I should have said that on the right-hand side, I'm just writing the contribution from a primary operator with respect to global conformal symmetry. But there is also contributions from the tower, from a full tower of conformal descendants of this operator. And now, the simplest thing one can do is to actually promote the conformal symmetry SL2C to a product of two copies of SL2R. So this amounts to the thing I hinted at the beginning, namely that it's convenient to think about the Z and Z bar as real independent variables. And upon doing so, one can resum the contributions coming from descendants with respect to one of these copies of SL2R. So what this is going to do for us in practice is that it's going to compute on the right-hand side contributions from subleading terms in a Z bar IJ expansion, right? And again, those contributions are completely fixed by conformal symmetry. And not only, I mean, not just their dependence on ZIJ, but also the OP coefficients. It's a fact, it's a known fact from conformal field theory that the OP coefficient of a primary operator, conformal plus conformal symmetry, determines completely the OP coefficients of all terms, all descendant terms. Okay, so this leads to this sort of expansion of a linear expansion of two positive helicity gravitons. So let's try to understand this expansion a little better. Well, what was noticed only in the past year is that this expansion actually implies something about the algebra of operators appearing at these negative integer dimensions that we argued before are associated to this tower of subleading soft theorems in the book. And so how do we extract the algebra of these operators? First of all, as I argued before, is to compute the residues of this formula in the limit when one of these dimensions, but in fact both of these external dimensions become negative. Now let's focus on the first operator. When we compute the residue of this right-hand side, when this delta I becomes a negative integer, we see that this infinite sum on the right-hand side truncates. So it's only going to have a finite number of terms. And this is a consequence of the fact I mentioned at the beginning that these Euler beta functions have poles at negative integer dimensions only. So we see that there's going to be a particular value delta A, delta J, sorry, that for a particular value of n and a fixed negative integer value of delta I, this coefficient is going to become positive, which means that when you compute the residue, we're going to pick up just a finite number of terms on the right-hand side. And now we can do the same thing for the second operator. And one arrives at an operator product expansion of two conformally soft operators, or two operators of negative integer dimension. Yes, which just involves a finite superposition of negative dimension operators on the right-hand side. So once we have this expansion, one can use the standard correspondence between operator product expansions in conformal field theory and commutators of modes that is given by taking particular contour integrals on the celestial sphere. And using that, one can extract an algebra of these conformally soft operators defined as the residues at these particular poles. The result of that calculation is perhaps surprising. What one finds at the end of the day is that one can associate these negative dimension operators, or in particular descendants of them, in a sense that it's going to become more precise later. So one can construct these this so-called W currents, whose algebra turns out to be this simple, to take this simple form. and can be identified as a W1 plus infinity algebra. So again, here the labels P and Q are associated to the particular conformally soft operator. So they can be related to these negative integer dimensions I mentioned before, while this M and N label the modes with respect to the anti-holomorphic expansion. Yes, so this is what formula means. Okay, so what have we done so far? Let's recap. So we have started from sort of leading collinear theorem in the bulk. We have written down the leading term in the operator product expansion of two gravitons. And then we have used conformal symmetry to resum the contributions from all of the descendants to this OPE. Okay, so we have then seen that for particular negative integer dimensions of these operators, the sum truncates. And I haven't shown, but one can then use that to compute the algebra of these negative dimension operators in the celestial conformal field theory. And one arrives at the perhaps striking result that their algebra of some particular operators that are related to these negative dimension modes by particular transformation, which again, I'm going to come back to later, that algebra is a higher spin symmetry algebra. So if you take a step back, it's perhaps surprising because this is supposed, I haven't assumed anything about the bulk in this calculation. All I have done is to start with the theory of gravity, with just Einstein gravity in the bulk, and just use conformal symmetry on the boundary to resum these contributions. And we arrived at perhaps a surprising statement, namely the fact that there should be some sort of higher spin symmetry just in Einstein gravity. So, yes.
Maybe where does the three-level assumption?
Yeah, that's a great question. So I should say that the three-level assumption actually enters here. So if you include loop effects, one can show that there's going to be log contributions in Zij to this operator product expansion. So the logs are dimensionless actually. And so in principle, just conformal symmetry will allow for such terms in this expansion, but I have not written them down. And in fact, that's an interesting question that I don't think has been studied yet. Namely, like to see like what those contributions would look like, which I think is pretty simple to do, but then kind of understand if those follow from some symmetry argument in this conformal field theory. That, yeah, none of that has been done so far.
So the shape of one loop correction, or actually all loop corrections, is completely constrained by conformals.
I don't know about that. I don't know. No one has done that before. All I can say about that is that loop corrections to the splitting functions, they have appeared in the literature since the 90s. So one can, and it's clear that they will involve logs of Zij that essentially come from logs of the Mandel-Stanley variants in the bulk, which we know are generated by loop corrections. And one can translate them into corrections in the OPE, which a priori in the bulk, they look very complicated, but actually on the celestial sphere, all they will do is to like generate some corrections to the leading OP coefficients and also generate some terms that will have these logs of Zij. And then one can try to understand. And there's been a recent paper where those loop corrections were actually studied from a like twister perspective. They've been shown to, like, for example, they were argued that they spoil associativity of the OPE, but the associativity of the OPE can be restored by including a particular axiom mode in this twister theory that is supposed to generate these OPEs on the celestial sphere at the end of the day. But that's a very recent paper, and I think there's like there's also other basic questions that one can ask about, which I don't think I've been studying. But yeah, that's a very good question. Thank you.
It was only global conformal symmetry.
So yeah, that's right. Here I'm using global conformal symmetry, and these are global conformal primaries. It's also actually interesting to understand how to reorganize this in terms of Virasoro logs and whatnot.
But you don't need the Virasoro.
For this analysis, no. At the moment.
So this derivation goes through in higher dimensions as well.
Yeah, this term should go through in higher dimensions as well. I don't see any obstruction in generating. Yeah, because in doing the same thing in higher dimensions.
You get into trouble with this modus in Ojibwe theorem.
Which
So in for like a 3 dimension, I think 3 dimensions are higher. you have these higher spin symmetries. I thought that Mollison and Jacob showed
Oh,
that
that's
there
the
were large
conformal.
constraints on the structure of the theory.
Oh, you mean
It's
the fact
specifically
that
for
if you have higher spin symmetry, but if you have like one higher spin current, you have to have the whole power of
Yeah.
higher spin currents, and then that imposes that the conformal theory has to be free.
Yeah.
Yeah, no, I think that would be interesting to understand. But yeah, that's an interesting question. But those currents will presumably, since there's going to be corrections to these OPs in the full theory.
Yeah.
But I guess they also have statements about approximate conservation laws.
Yeah.
So yeah, yeah, that's interesting. I don't know. But there is, anyway, I'll comment at the end. There are
Okay,
some
yeah.
other papers that maybe have some related things in them. But yeah. Any other questions? Okay, so then in the last 15 minutes, I'm going to try to actually describe to you what we did. So how do we see the symmetries in 4 dimensions? This is the question we stopped at. And how come there is this higher spin structure in just Einstein gravity? So to set up that problem, one has to take a step back and think about how people usually describe asymptotically flat spacetimes in 4 dimensions. And it turns out that it's convenient to express them in so-called Bondi gauge. So what is this Bondi gauge? This is a set of coordinates that is adapted to the study of gravitational radiation, again, known since the 60s. So what this Bondi gauge does for you is it picks a particular set of coordinates so particular choice of R, in which the waves, gravitational waves, propagate radially outwards. Moreover, the wavefronts are spherical, and then one can construct solutions to the vacuum Einstein's equations that take this general form shown here. And this solution typically takes the form of an expansion in a large parameter, which is R, or the distance from the source of gravitational radiation, right? So one should imagine this case as, for example, having some sort of like black holes in the bulk that are merging or whatever, some source of gravitational radiation, and the solution should be interpreted as how the metric at infinity will look like for this particular configuration. So there's going to be some kind of gravitational waves that reach infinity and modify the structure of space-time. So there's going to be perturbations surrounding off the space that will fall off in a particular way with R, okay? And so the main parameters of this solution are the gravitational potential. So that turns out to be related to the so-called Bondi mass. So the Bondi mass is physically, it tells you how the net mass in space-time, how it changes with time. So for example, if you have these 2 black holes, for example, you can have a situation where the black holes are evaporating, so there's going to be radiation that goes to infinity, and so the mass of the system typically decreases in time as a function of returning time. So this is what physically the Bondi mass measures for you. Then there is this epsilon function that similarly captures the flow of angular momentum. So the angular momentum captured by, captured by the gravitational radiation. And then there is this gamma AB here, which is the full transverse metric. So to sort of first non-trivial order in a larger expansion, that is just the graviton. It's a perturbation around the Minkowski background. So you should think about this CAB as the shear and its time derivative. So the shear of the transverse metric and the time derivative of it is called the news. And this news, it's squared rudder. It's related to the flux of gravitational radiation through null infinity. And so order by order in a larger expansion, one can expand these functions. And so, for example, the gravitational potential, the gravitational potential will take this form, and these functions here, they will be constrained by Einstein's equations. Yes. So in practice, okay, this slide looks a bit ugly, but one can fix these terms in a larger expansion by Einstein's equations, in particular at order, if one studies Einstein's equations at order 1 over r squared, and looks at the Einstein tensors, the UU component, UA component, and AB component. So, sorry, I should say AB here are transverse indices, indices in the transverse space-time. There is a retarded time U, a radial component R, and then there are these transverse coordinates on the sphere. So the GUU component leads to this particular order, one over R expansion. It leads to an equation that constrains the evolution of this body mass aspect as a function of retarded time U. So physically, this makes sense because we can take an integral over U of this equation and then also over the sphere. So we can compute the body mass as a function of retarded time integrated over the sphere. In that case, this first term drops out, and then we just find an integral over the square of the news. And because of this minus sign, you see that the body mass decreases as a function of time, which is the statement that the thing in the bulk evaporates. And so this is sort of the physics of this first equation. And now there is similar kinds of equations for the for the angular momentum aspect. Again, it's a bit more complicated, as you can tell here. And there is a similar equation in the same order in a 1 over R expansion that governs a particular component, a particular subleading component of the transverse metric. And I should point out that this equation for this component, it's a 1 over R component in the transverse metric GAD. And it is, it's a 1 over R component in the joint R squared gamma AB metric. And its evolution, note here that it's actually quite complicated because it depends on this n, which is the angular momentum aspect. So to actually solve this equation, one would have to go back to the previous equations to express it all in terms of the news. And so it's going to become sort of a bit of a mess. And the question is, okay, so what is the phase space? And here we think that the phase space consists of the news, certainly. So there are these two conjugate variables in the phase space. One of them is the news, it's unconstrained. Then the other one is this shear. The derivative of the shear is the news. This can be thought of as some kind of coordinate and angular momentum operators, conjugate variables in the gravitational phase space. And then perhaps there are these boundary values of the body mass, angular momentum aspects, and all these other components that would arise from a lower limit, from a boundary condition for this integral over retarded time. Yes.
Perhaps it's a naive question, but since we're making these large R expansions,
yeah,
and R is a dimensionful parameter, and we do not have like natural length state, should we be worried? I mean, should we be worried about that, or we can simply, is there a reason we can ignore the fact that we don't have a dimensionless parameter we're making the expansion?
Actually, in a moment, I'm going to make use of that to actually reorganize this expansion according to the dimensions of the things that appear in the bulk. And so, yeah, so maybe it's going to answer your question in a second. Because I'm just, so far, I'm just flashing like the standard story, like how it's been done. And actually this equation for this particular piece in the transverse metric has only appeared relatively recently and has not really been exploited so much. But we're going to see in a moment that this equation is going to be crucial in establishing a correspondence between the subleading self-gravitance theorem and some conservation law of some churches. So, yes.
The quantity EAB,
yeah,
subleading quantity.
Yeah.
Does it appear in the symplectic form?
Yeah, so that is a good question. I would say right now that here, by saying that the phase space is this, is a bit of a lie, because what we can show, but it's not, the paper is not out yet, we're working on it right now. What one can show is that the symplectic form for N and C can be traded for a linear combination of symplectic form, like of terms that involve all of these subleading components in the metric. So in some sense, the phase space, at least the phase space we're working with, does not contain both A, N, and all of these charges, but one can trade the symplectic, one can trade the N and C variables for a linear combination of terms that are canonically conjugate, and one of them is going to be this EAB.
Yeah.
But not the EAB. You'll see. I'm going to trade these variables in a second for something that's for some variables that seem more appropriate. So, all right, this is standard story, but at the beginning, I kind of said that perhaps it's more useful to think about, to organize observables in terms of according to symmetry. And the symmetry that stands on a very firm footing of asymptotically flat spacetimes right now is the so-called extension of the BMS rule. So this is an extension of the naive Poincare symmetries one would expect in four-dimensional asymptotically flat spacetimes to include angle-dependent translations of the spheres of cross-sections of the null cones at infinity, together with angle-dependent Lorentz transformations. So these Virasoro symmetries. So these are the standard symmetries that we know asymptotically flat spacetimes have. And we know that they are associated to non-trivial charges because we know that there are observational consequences of these symmetries, namely through soft theorems and memory effects and so on and so forth. And so here is just very briefly, these symmetries are labeled by particular vector fields. So this is some diffeomorphism that preserves physically chosen particular asymptotic boundary conditions on this metric, on the solution to Einstein's equations I wrote down before. So this is a diffeomorphism, and it's labeled by a function f, a vector field y, and another function w on the sphere. So this having just a non-trivial f, but 0, y, and w, that corresponds to super translations, to just restricting to a sector where you just have super translations. Then if you set f to 0 and non-zero y and w, that corresponds to super rotations or these Virasoro-like symmetries. And so this is what we have. And as we can see, this vector field doesn't fall off with R, so it has a non-trivial action at scry. So this is important. And so and of course one can associate these vector fields with charges, as I said at the beginning. But now, what I mean by organizing asymptotic data according to symmetry, I mean to construct particular linear combinations of the fields that appear in this larger expansion of the metric I showed before, that transform nicely under the action of this symmetry. And by nicely, you should just take this as the definition. I mean this, that when I compute the d derivative of a particular operator constructed from these asymptotic pieces of the metric, that the action of this is just the d derivative with respect to y up to some factor that depends on two parameters, which we call delta and s, and they are to be determined from the transformation property. And these are, so this is related to Felipe's question, this delta sort of corresponds to a dimension from a bulk point of view. And r and u on all of these coordinates I mentioned before, they can be assigned particular dimensions. And these operators that appear as coefficients in a larger expansion, they should have dimensions such that they match, such that the expansion is consistent from the dimensional analysis point of view. And so as an example, what one can show by just computing the d derivative action, for example, on the Bondi mass, is that the Bondi mass itself won't obey this nice transformation property. But however, one can construct an object, which is a particular linear combination of the Bondi mass and the product of the shear and the news, and that actually does transform nicely. And it obeys this equation with delta equal to 3 and s equal to 0. So this is a space-time scalar, as you can see here from the index contractions, and it turns out to be an operator of dimension delta, just from this definition. Delta equal to 3, sorry. Okay, and one can proceed by doing this to fixed order in a 1/r expansion and construct all quantities that can appear that obey this nice transformation property. And what one finds is that not just the Bondi mass, but also the angular momentum aspect and the subleading component of the transverse metric can be traded for some new quantities. So far we're calling them Q0, 1, and 2, all of which are dimension delta equal to 3, and they are space-time scalars, and they obey this equation. well, you may wonder why they're space-time scalars, because clearly this News tensor and this transverse tensor, they have helicity plus or minus 2 in the bulk, and sorry, plus or minus 1 or 2, so they're not really scalars, but these charges actually, what we do to construct them, we contract them with particular frame fields in the bulk, which turn them into space-time scalars, but these frame fields actually do have non-trivial transformation properties, conformal transformation properties on the sphere. So we're trading bulk vector fields or tensor fields for for particular fields of particular helicities on the celestial sphere. So okay, so the take-home message at this point is just that the mess of those equations I showed on one of the previous slides actually just simplifies quite a great deal, in the sense that now these three quantities that can transform nicely under this extended BMS group just obey a set of recursive differential equations that just take this very, very simple form here. So we see, so at this point, I'm only letting S run over 0, 1, and 2, and I can extend this series to include a Q minus 1 and a Q minus 2 that are just simply related to the News tensor, or rather the contraction of the News tensor with these frame fields on the sphere. So, so we have the set of recursive differential equations, and now we can integrate them to find the solutions for these charges. And to do that, we need to impose some boundary conditions. And it turns out the convenient boundary conditions are to impose that, well, we need the particular boundary conditions on the News as it falls off as a function of retarded time. Because as you can tell from this recursion relation, if I want to solve for the charge, for example, for Q2, I would have to integrate over retarded time. So this dot, sorry, I should say that the dot means derivative with respect to retarded time. So if I want to express Q in terms of Q minus 1 or the News, I would have to perform several integrations, so 3 integrations. And in order for that object at the end of the day to be well defined, I need my Q1, which is essentially the News, to fall off in a particular way. And so once I've done that, I have expressions of all of these charges that are completely determined in terms of the News. Then I can use the standard canonical commutation relations, where we just have a phase space that is not enhanced, but it's just a simple one, including the News in the sphere, and compute the action of these quantities on the phase space, which gravitons, for example, so namely the brackets of these charges with the shear. And indeed, when one does that, one can show that the conservation law for these charges, for the S equal to 0 and S equal to 1 charges, by conservation, I mean the fact that I'm matching the charges across spatial infinity here. So I'm assuming that there is no flux going off through I0. The matching condition is essentially the statement that there is no flux going off through the sphere at spatial infinity. And that leads to a conservation for these charges in time. And to combine with the action of the charges on phase space, one can show that this conservation law is equivalent to the soft theorems. What's interesting here is the fact that the S equal to 0 charge, the S equal to 2 charge actually turns out to give rise to the sub-leading soft graviton theorem, which was not established before. Now, to do that though, one needs one additional element, namely one has to renormalize charges, these charges, these QS's, because when one computes the action of these charges on phase space, it turns out that their actions are not well defined in the limit as one takes u to minus infinity. Or in other words, these big Q quantities, they don't obey this no flux condition to I0. So one has to define new objects that are such that their derivatives with respect to time have actually vanished at very early retarded times. And so that thing is implemented by this renormalization procedure here. And so it is these renormalized little Q charges that actually obey these conservation laws I mentioned before. So, so for S equal to 2, there is a new conservation law, which is equivalent to the sub-leading soft theorem. And let me just show you Okay, I'm out of time, but the way that works is just simply, I've given you a recipe of how to construct these charges, so you can now express them in terms of the News tensor, and you can compute their action, as I said before, on the shear very explicitly. It's just a matter of calculating it, and you get a complicated expression that looks like this. And to relate to the soft theorems, it's a bit of a, I mean, if you haven't followed the story, Johan has to go through a couple of steps, but one of the main steps is to take a Fourier transform with respect to retarded time. So to go from position space to momentum space. And it turns out that this first line here turns out to be completely equivalent to the sub-leading soft graviton factor, whereas this piece here can be shown to correspond to the insertion of the sub-leading soft graviton. So in that sense, the matching, one can establish a relationship between the matching of these S equal to 2 charges and the sub-leading soft graviton theorem. What we found a bit interesting was the fact that there is also an additional contribution here to the to this bracket. So this is a nonlinear contribution, which suggests that there is a correction to the sub-leading soft theorem that has only contact support. So one can show that these two operators here, they will be actually collinear, right? You see that they lie at the same position on the celestial sphere. So that gives rise to a delta function contribution to the sub-leading soft theorem, which previously, since people work usually in this formalism where one treats Z and C bar as the real independent variables, that was missed before, but it would be interesting to try to understand what this means for the sub-leading soft theorem. Okay, and just so to sort of wrap up and say kind of where this is going, now we can remember this recursion relation, which one can very explicitly for S equal to 0, 1, and 2 match to the Einstein equations that slide, that like messy slide I showed before. But one can wonder, okay, what if we take this recursion relation and extend it to all integers S that are also greater than 2? So one can study the implications of this infinite set of charges and go through the same procedure I mentioned before. And in particular, one can show, okay, so at each level S, one thing to notice is that these charges, they have, they're very nonlinear. They have a linear term in the fields, they have a quadratic term in the fields, but at level S, they will have terms of order S plus 1. So it comes from the nature of this recursion relation. And so the idea is to take this expansion, truncate it to quadratic order in these charges. These higher terms will correspond to collinear contributions to the soft theorems, which so far we're ignoring. But the point is that one can compute again the charge actions, and one can compute what the conservation law means when inserted into the S matrix. And it turns out that what it means is that it reproduces precisely this power of soft theorems that I showed before that was found from this celestial OPE perspective. And so we have, what this tells us is that we have a map between the currents I showed before, these negative dimension operators in the celestial conformal field theory, and some particular components of the asymptotic metric in a larger expansion that obey this differential equation, which I should say that it's related to Einstein's equations asymptotically. And so the fact that the two match is in some sense holographic, in the sense that we have a way of computing some Ward identities in the celestial conformal field theory, and that implies a set of in some sense dynamical, I mean asymptotic dynamical evolution equations for some objects in the volume. So finally, what one can do is to compute the algebra of these charges, again, just using the canonical commutation relations. And it's we so far have done it to leading order and in expansion. So remember, these are nonlinear quantities. If you truncate them and compute the linear contribution to this bracket, one finds that they indeed obey a W1 plus infinity algebra. And as I said before, so this matches, of course, this matches the algebra that was found in the celestial conformal field theory to be obeyed by these W currents. And now, I mean, one can say, sort of mentioned it before, that one can turn the argument around and show that, and kind of argue that once you have the celestial OBE, one can infer from it the existence of these dynamical evolution equations that take this form. And in some sense, you can perhaps, if you want, you can think about this as a holographic prediction for asymptotic charge dynamics in four-dimensional gravity and asymptotic. And so to summarize, I have shown that one can use this extended BMS symmetry to reorganize asymptotic fields into so-called primaries, into some objects that transform nicely under these asymptotic symmetries that allowed us to recast the asymptotic Einstein's equations into this simple form of recursion relations. We can show that we can solve these recursion relations by imposing particular boundary conditions and this no-flux condition that leads to some renormalized charges. We showed that these charges, then their conservation implies this tower of soft theorems or ward identities derived holographically. And we have also shown that there is a precise map between these charges in the bulk and these celestial W currents. And so this is a signature of how Einstein's equations, or a piece of the asymptotic Einstein's equations, which I haven't quite had time to describe in detail, but evidence that these ward identities found holographically, so in the two-dimensional conformal field theory, encode some information about the evolution equations, so Einstein's equations in the bulk. So then there are a bunch of future directions, and one of them is to try to understand the full algebra of these nonlinear charges. So we're working on this, and there seems to be some interesting evidence that this algebra persists at nonlinear order. So perhaps there is a special property of these recursion relations for these charges that suggest more mathematical argument that they have to generate charges that obey such a higher spin symmetry algebra. Now, I haven't mentioned subtlety, namely the fact that beyond s equal to 4, there are going to be corrections to this recursion relations. So these recursion relations only capture a piece of the asymptotic Einstein's equations. There's going to be certain corrections, but there's similarly going to be the same corrections can also be seen in the conformal field theory, and they arise in operator product expansions involving mixed helicities. So if you remember here, I have focused on equal helicity OBEs and derived all these facts for, say, positive helicity gravitons. But if you take OBEs of positive and negative helicity gravitons, there's going to be corrections to those OBEs, and those should be matched to corrections to Einstein's equations and corrections to these recursion relations I showed before. It hasn't been done yet. Then there is an interesting relation between these charges and so-called light transforms in this two-dimensional conformal field theory. These W currents I haven't really mentioned, but they are actually related to the negative dimension operators by so-called light transform. And the only difference is that the charges obey operator product expansions that have contact singularities, whereas the W currents obey sort of operator product expansions that just have poles in the IJ, and it would be interesting to understand the connection between those two pictures. Formal level, they should be the same things because they have the same conformal dimensions. Then there are questions about, some of them have been asked about quantum or higher derivative corrections to these OBEs, and how can we understand the precise map between those and corrections to these equations of motion. And then there is a big question about how the symmetries act. One can show that they actually don't act as diffeomorphisms, at least at infinity. The symmetries associated with these higher spin charges have a very non-local action on scribe, but they may be related to a particular kind of so-called overleading diffeomorphisms that appear and have been proposed before to enhance the symmetry group of asymptotically flat spacetimes. And then there are connections to memory effects, to what extent the charges are observable. So since they capture the gravitational radiation, they are naturally related to this so-called memory effect, which is an observational consequence of the signature. And these memories should be labeled by these charges. And they have been, at least the leading memory effect has been proposed to be measured at this space gravitational wave interferometer. matter, and so it would be interesting to understand how signatures of radiation are labeled by these charges. And there's many other questions I'm happy to discuss more, but I'm already out of time. So thank you very much.
We have some questions.
Maybe just a really general question. If I think of just different examples of gravitational theories, are there, so is all of this basically universal, or are there things that, what would be different in different examples, I guess?
Yeah, so what the thing that would be, so this has not been done before, but what would be different? I should say that at the linearized level, we can show like very explicitly that the truncation to this equation, right, this term is not going to be here because it's quadratic. This thing just follows, it's just the linearized asymptotic Einstein's equations. It's the evolution of the file tensor to all orders. You know, it appears at all orders in one over R expansion. You can establish precise relation between that. This is just pure Einstein gravity. Vacuum Einstein's equations at linearized order, they're just this piece of the equation. Now, this plus other higher corrections, they would correspond to pure Einstein gravity in all, you know, with mixed helicity sectors, you need to add to this equation some terms that would involve C bar. That has not been worked out yet, but also it hasn't been worked out in the celestial conformal field theory. So these equations are not even pure Einstein gravity. They are a particular truncation of Einstein's equations in equal helicity sectors. If you want to mix helicity sectors, there's going to be some corrections. Now, if you want high derivative corrections, those presumably will also modify these equations, but in a way that's consistent to the corrections one would expect from high derivative operators to the soft theorems. So this is like higher derivative, these are all classical things. Now for quantum corrections and so on, it's beyond, these are just classical solutions at this point. But yeah, one would expect modifications to both the ODE and these recursion relations, but in such a way that the two should match. So perhaps, I mean, one way forward it would be to understand how these higher derivative corrections look like in the selection conformal field theory, because those can be presumably fixed by symmetry, as long as the OPEs are associative, which I would say is a bit of a subtle problem. But once one figures out how to come across an associative OP in mixed helicity sectors and including higher derivative corrections, it should be straightforward to compute those corrections, and those should map to corrections in these equations. And I mean, in that sense, there is this interesting, I'd say, relationship between dynamics and the bulk. And and these OPEs. And again, I should emphasize that this you start seeing into the bulk, because these charges at higher levels S, they can be shown to be related to coefficients of subleading terms in a 1 over R expansion of the asymptotic metric. And so if you keep adding those, it's like you're starting to see sort of into the bulk a little bit.
But Einstein gravity means that your amplitudes are looking at the scattering amplitudes of our drop. Can it be heavy matter or just?
That is this is a great question. So if you also add matter, that would also modify these equations. So here I was restricting to the sector where you just have pure gravity, so essentially just hard gravitons.
So even massive matter?
Massive matter, okay, so it depends on what question you're asking. I would say that it has been not so much studied in the celestial context. There is a formalism to also include massive. One can in principle write down celestial amplitudes of massive particles as well. And there should be a sense in which those, if you include massive particles, you would also be able to write down some operator product expansions, but there is a bit of a subtlety there in the sense that massive particles, at least naively, appear to be non-local on the celestial sphere. And so their operator product expansions with, say, gravitons or soft gravitons, they won't take the simple form I showed before. So like, yeah, they won't, if one of these operators here was massive, then this thing wouldn't be as nice. There would be some kind of non-local corrections on the right-hand side. it is naively, but there may be a way to redefine those massive operators by perhaps addressing them with some fields, which would absorb sort of, and so like find some local operators. So I'd say that it's an open problem to find some kind of local operators associated with massive particles, local operators on the sphere. But nevertheless, I mean, it should. I want to think that that should be a doable. I mean, it should be a doable thing. Yeah, which would be very nice because it would then clearly, I mean, would go sort of beyond the twister sort of methods that in which is a bit more difficult to include massive particles. But here there is a path forward, I would say, but it just hasn't been explored so much.
Just going back to the symplectic form. So it's the symplectic form was that so the delta the shear wedge delta used.
Yeah, that's the symplectic form we have here.
And this one is the one I get if I impose the usual boundary conditions for.
Yeah, yeah, that's the usual.
And it is this symplectic form that you use to compute.
Yeah.
Chemical.
Yeah.
And so these charges you find they're all written in terms of these two objects, so the shear.
What we find, so again, this is still work in progress, but what seems to be the case is that the usual symplectic form has a decomposition into a linear combination of terms involving the star of charges and terms that are conjugate to those charges, which we have not addressed here at all. Those would correspond to positive dimension operators on the sphere.
So but that's a change of variable, right? To go to this, because you still start from delta C with delta N. And the change of variable, like, do you do it through the equation?
Yeah, there is a simple guess. Well, maybe I can show you later what you do, but basically you expand, you consider. There is a very precise formula that allows you to write down a particular this soft charges, the linear charges that involve some integral. It's some Mellon transport with respect to the u variable, and then you can take a Taylor expansion of your shear in parts of u, and then essentially what you see is that the symplectic form for C and N can be written as a linear combination of symplectic potentials for these linear subleading charges and the coefficients in a Taylor expansion of the shear, but those coefficients are precisely the things that shift under the action of the soft charges. So these are the Goldstone modes associated with these symmetries. And so yeah, so there are two. Yeah. Anyway, I can show you explicitly later.
I'm assuming because it looks like these symmetries cannot come from. I mean, in the usual analysis, it looks like it can come from other type of morphism than BMS, because the BMS group is by definition the thing that preserves the boundary conditions you chose, and that gave you this symplectic form in particular. So these overleadings, what are these overleadings?
Yeah, so those overleading, yeah, they have there's different boundary conditions people have proposed in the literature. And in particular, so here I should have said, yeah, you already know that, but here we start off with particular fallouts for all the components of the metric, and roughly speaking, fallouts that allow the passage of gravitation, radiation, and whatnot. But there's been a proposal that one should allow for overleading. So the metric here, you see like manifested, the transverse metric starts off at order r squared. But if you allow an order r cubed term in it, that would correspond to allowing for large gauge transformations that are not order 1 inscribed, but they're order r. And there's been a paper in the past where just in theories of scalars coupled to gravity, it was shown that if you construct some charges from a covariant space formalism, just using that the recipe, covariant space recipe, and plugging these overleading diffeomorphisms associated with some charges. And you can show that the conservation of those charges reproduces the subleading self-graviton theorem. The two charges. So first of all, that analysis has not been done in pure gravity. Secondly, the charges that were obtained in that paper, they're pulled back on strictly on scribe. Oh, and sorry, I should say that procedure also requires some renormalization of the charges. So those charges now have terms that grow with R, and those have to be removed. But there is a consistent way of doing that. And then you arrive at some finite charges that should agree with the charges which we have written down from the Einstein equation. So I should say that our charges were not constructed from a covariant space formalism, and in particular, naively, the things we have, the charges we have, if you want to associate them with a symmetry, that symmetry won't be a diffeomorphism. It has non-local actions, right? It involves inverse derivatives with respect to time. Is this so there's pseudo vector fields that appear in this analysis in the remote systems. But yeah, but I'm saying that these charges on Scry, they agree with some charges constructed from some covariant space formalism associated with these overleading diffeomorphisms. And it would be interesting to understand. I mean, for me, right now, it's very hard to see how these vector fields should obey a higher space symmetry algebra, and it's hard to see how diffeomorphisms would obey such an algebra, right? So, but something happens in this perhaps normalization procedure involved in that paper that kind of. Well, I have some. I just need to. I have some guesses about that. If people are interested, I mean, I think. But yeah, it's an open. At the moment, understanding in what sense these are symmetries or like local symmetries in the bulk. Maybe they're not local symmetries in the bulk because they seem to be non-local. They're yeah, what's local in this two-dimensional theory seems to be non-local, vice versa. So just stories.
And I have a small question. So it's going to be related to what Mark said. Do you confuse of central extensions with this W1 plus something?
Yeah, that's a good question.
They exist.
Yeah, presumably. I mean, some people would want to say, if you take this symmetry very, very seriously, you may want to say that perhaps, you know, there is just a finite number of quantum deformations of these double infinity algebras, and somehow quantum gravity in four-dimensional asymptotically flat spacetimes, whatever that is, correspond to one of those quantum deformations. I'm not sure if I necessarily, I mean, to me, it seems like a very optimistic point of view, but yeah, I mean, it would be interesting to understand. But I don't think anyone has tried to. And not to mention match one of the known quantum deformations.
Okay, I think we can thank Anna for this beautiful talk. It's going to be around until Wednesday. She's in my
Thank you.
Yeah.